Hello, discrete math fans. Let's prove this statement. For all n in the integers, if n is even and n is between 4 and 26, then n can be written as the sum of two primes. Here's our solution. 4 is 2 plus 2, 6 is 3 plus 3, and so on. We just write down for each even integer between 4 and 26 how to express it as the sum of two primes. Notice that in some instances, these aren't the only way of doing it. Like here, 20 is equal to 7 plus 13. 20 is also equal to 3 plus 17. We don't need to show every possible way of writing each of these integers as a sum of two primes. We just need to have some way of doing it. Now this method of proof is called the method of exhaustion. We just list each integer that we're interested in and show for each one specifically how to do what we're interested in. Now we only have to check 12 different numbers, so this is not too bad. What if the domain was really large? It could be tedious to do this, or it could be computationally difficult. What if the domain is infinite? Then this method is completely impossible. What if I asked you to prove that every even integer larger than 2 could be written as the sum of two primes? Well, this would be impossible to do by just listing all the even integers. You can't possibly do it. This is actually an open question in mathematics as to whether or not every even integer bigger than 2 can be written as the sum of two primes. This is called the Goldbach conjecture, and it's been theorized for hundreds of years that it's possible to do this, but nobody's been able to prove it. All right, so how do we show the truth of a statement such as, for all x in D, p of x? And here we're supposing that D, the domain of the predicate variable, is a very large finite set, or maybe even an infinite set. So we actually have a very powerful method that accomplishes this. This is called the method of generalizing from the generic particular. Now nobody's going to ask you to memorize the name of this method. It's not going to come up later on, but you do need to know the method. The method is actually very important. It's the name that you don't need to worry about. It says that in order to show that every element of a set satisfies some particular property, we suppose that x is a particular but arbitrarily chosen element of the set. And then we show that x satisfies whatever property we're interested in. So as an example, let's prove that the sum of any two odd integers is even. Now let's restate the problem using formal logic. We'll let D be the set of odd integers, and we'll let E be the set of even integers. This will just help us with the notation. Our goal is to prove that for every m and n in the set D, m plus n is an element of E. Now we're going to choose arbitrary odd numbers. Now we cannot go around choosing particular odd numbers. We don't want to actually deal with any numbers. Like we can't mess around with 3 or 5 or negative 17. We have to make an arbitrary choice. So let's let m and n be elements of D. Now this is our choice of particular but arbitrarily chosen odd numbers. We're not going to say what m and n are. They're arbitrarily chosen. So then, m can be written as 2p plus 1 for some p in the integers, and n is equal to 2q plus 1 for some q in the integers. Now we can say that m plus n is equal to 2p plus 1 plus 2q plus 1, and we'll rewrite that as 2p plus 2q plus 2, and then we factor out the 2. Now we know that since p and q are integers, p plus q plus 1 is also an integer. This is just a property of the integers that we accept, that when we add integers, we still get an integer. So therefore, m plus n is even, because we have expressed m plus n as 2 times some integer. And remember, that's the definition of what it means for a number to be even. Now there's a point in this proof where we asserted the existence of P and Q, here and here. This is a technique that's called existential instantiation. We knew that M and N were odd numbers, and therefore there was this P and Q that existed. So the definition of odd integers says that such integers exist, so we can give them names and then use them in the proof. So existential instantiation, again, another name that we're not really going to need to know, but we're going to use this method a lot. It says that if the existence of a certain kind of object is assumed or has been deduced, we can give it a name, as long as we don't use that name for something else. Okay, that's all for now.